And what I want to do is to take you through a journey which is long, because experimental physics is long. When you are embarking in experiment that you are the only one to do, you have to face many unexpected difficulties, but it is a pleasure of experimental physics to really surmount these difficulties and at the end to get results. Before starting, we already cited Dominique Delalande. Dominique Delalande was a fantastic collaborator for us. He was a great expert in calculating in numerics everything you want to calculate, and it was a great loss. And Marcel and I, we know that until the last days, Dominique, in fact, he was fighting his disease by trying to concentrate on the kind of problem he was having, in particular with us. Okay, let us go on. So we have this group of people working on, as we say, quantum transport in Institut Optique, and the head of the team is Vincent Josse, and the guy who is really responsible for the recent results that I will present and who presents a poster here is Shudong Yu. He knows everything. You can ask him any question, and I'm sure you will know what you want to know. Just one word about quantum simulation, which is a domain in which my group in Institut Optique started like 2 decades ago. The idea was to understand the system of many particles, which is absolutely impossible to describe and least to study on a classical computer. You know that Feynman wrote a paper about that in 1982. And for instance, if you want to describe the electrons in a piece of solid, forget it with a standard computer. So quantum simulation consists of mimicking the system to study with other quantum particles, easy to manipulate, to observe, and with parameters that you can easily modify. And it's not only mimicking a system that you have. For instance, suppose you want to mimic a piece of metal. Well, in that piece of metal, the density of electron is fixed. There is not. While in simulation, you can decide to divide by 2 the density of particles, etc. There are plenty of possibilities opened by quantum simulation. And so our favorite quantum simulator is ultracold atoms in synthetic potential created with laser beams. And with that, you can change density, you can change the potential parameters, you can even change the shape of the potential, and you have many observation tools that you don't have if you have electrons in a piece of metal, for instance, and I will show you a few of them because I want to share with you the enjoyment of and the pleasure to have all these tools available. Then first, I'm going to present I think I am brave to say that I'm going to present Anderson localization, but don't expect me to present Anderson localization like theories do. I will tell you my naive vision of Anderson localization, which I use for intuition of things to do with it. So this is the way I understand the problem of Anderson localization, and my reference here, it's paper of Mott in the 1950s. And the basic problem that they wanted to address is the following. When you have a classical model of metal, you have the electron bumping on impurities, and so you have a limited conductivity. And as soon as you increase the number or the density of the impurities, conductivity decreases. But in the classical model, never goes to 0. And there are instances where it goes to 0. And as Mott say, we have to understand that. And among the various models for trying to understand how conductivity can be totally to 0, there was a Mott model, but there was the Anderson model. And so Anderson found this model where disorder can totally cancel conduction. And he did that with a tight binding model with disorder. I will show it in next transparency. And the important thing is that there was this approximative called the condition, the Joffe-Regel model, which says that this localization should happen if the mean free path is of the order of the wavelengths of the matter wave, which is basically this condition. It tells you that the de Broglie wavelengths should be longer than the mean free path between the particles. This is not comfortable, but I am going to do it. Now, this was explained to me by Boris Altschuler. I was telling Boris, look, Boris, I would like to understand what is the relationship between the model of condensed matter people and the way we people in AMO optics understand localization. And he showed me that there is an equivalence here. But don't try to look for a paper where he wrote that. When I asked him, did you write that? He said, oh, come on, you know, Alain, this is what I call oral teaching. I'm not fully sure. Okay, so for condensed matter people, the Anderson model is quite simple in principle, not simple to solve. You start with a tight binding model. You have electron in a perfect crystal. You are in a domain of extending wave function, so the electron propagates freely in this. And then Anderson introduces a disorder by making small fluctuation, small variation, I should say, in the bottom of the well, and he shows that as soon as the disorder is large enough, it's characterized by that. Rather than having an extending wave function, you have a localized wave function. This is a vision of people in condensed matter. The vision for people like me, working on wave, optical wave, or matter wave in this atom optics group. Okay, when we are in a free medium, no absorption, nothing, we have a wave propagating like that. And then as soon as we have many scatterers, I have multiple scattering, and if I have enough multiple scattering, at one point, I have a localized wave function. Where does it come from? Well, the naive image is, but I think it's very fruitful because it guides the intuition, is the following. You have the wave arriving and a scattering on a first scatterer. And then, of course, there may be multiple scattering, and over the various multiple scattering trajectories, you consider trajectories coming back to the origin. If all these waves coming back to the origin come in phase, there is reinforcement of the wave at the origin. And now, what is a condition for all these waves coming in phase? Well, there is a very simple solution. If the length of the trajectory is small compared to the wavelengths, let's say not more than 1 radian or something like that, they basically come more or less in phase, and then you have this. And so the mobility edge, once again, is of the order of mean free path, definitely smaller than the de Broglie wavelengths, where the criterion is de Broglie wavelengths divided by 2 pi. Why do I like this picture? Because it allows me to immediately understand many features. First, the Anderson localization comes from interference between many scattered wavelengths. This is this interference that leads to localization. Second, it has to be clear that it is a single particle effect. Okay? If I have a single particle, there is only one matter wave, and it is multiple scattering of that matter wave that provokes localization. And then maybe the most interesting part is the role of dimensionality. Because, you see, it's all a question of returning to the origin, okay, in a Brownian motion or something like that. And this is a well-known problem. Returning to the origin in 1 dimension is very easy. Returning to the origin in 2 dimensions is not so easy. Those of you who play golf know that it is not so easy, okay, to come back to a hole. And returning to the origin in 3D, playing golf in 3D would be a nightmare. You would never return to the place where you want to go. So I think that this image allows you really to appreciate why the dimensionality is so important in Anderson localization. The quest of Anderson localization with classical waves I've been a long time research, and it has been successful with microwaves, with light on 2 dimension or 1 dimension, with acoustic waves, but with light in 3 dimension, it has been a failure. And there is a paper by our friend, where is he, Sergey? He's somewhere here, Sergey. He wrote a paper with a page. Where the title was Red Light on Anderson localization, showing that it had not really been observed. And now he comes with a new proposal, and he claims that it can work. I have doubts. I told him why I have doubts. I think that the main problem with scattering in 3D is that because light is vectorial and transverse, it seems very difficult to achieve this interference. But he has a proposal. It deserves to be tried. Anyway, so the quest with classical waves was somewhat successful, but very difficult. And so we embarked into doing that with matter waves, that is to say, with cold atoms. And the disorder was a disorder produced by laser speckle. What are the good features? First, with ultracold atom, we can control dimensionality. We can have, I will show you example, we can have 1D, we can have 3D. I will not show 2D, but it's the same. The wavelengths can be varied over many order of magnitude. I cite here from the de Broglie wavelengths, depending on the velocity of the atom, can go from nanometer to many micrometers. Most important, we have pure potential. I will explain you why we have pure potential. So nothing like absorption, which is the absorption is a disaster when you try to observe localization with light. And we have many observation tools. I will show a few of you. And last and not least, for me, the fact that if we have a particle without internal structure, it's scalar waves, which makes, for me, the intuition work easily. Well, there is a problem. There is interaction between atoms. This is not the subject of this. It's just to say that there might be at least 2 other collaborations of Simons for studying this problem. It's future problem. Well, Svetlana does not seem ready to launch a new collaboration. Okay, well. Just, I flash, most of you know that, but maybe not all of you. What is the how can we manipulate atoms with a laser? The idea is quite simple. You have an electric field. Voilà. You have an electric field, and the electric field excites the dipole of the atom. And so the electric field couples to the dipole and gives rise to some potential energy. That's simple. And you have the polarizability here. And so at the end of the day, you have a potential which is proportional to the intensity of the light, and with a sign which depends on the sign of the polarizability. So here, for instance, if you focus a laser beam, if the frequency is below an atomic resonance, then the polarizability is positive, and you have a negative potential. A potential well. You attract the atom here to the focus of the laser. If, in contrast, you are above resonance, the polarizability is negative, and then you have a mountain, and the atoms are expelled from the mountain. Okay. C'est easy. Now, we want to put the atom in a disorder potential. We decided to use a laser speckle. What is a laser speckle? A laser speckle is what you obtain by passing a coherent beam, that is to say a laser, through a scattering plate, you know, ground glass, okay? And then here you have a disorder structure. And the good news about this disorder structure is that we know exactly how to describe it theoretically. And the reason why we are so sure of it, it's because an application of the central limit theorem. because you can describe it in the following way. The electric field that you receive here is the sum of many wavelets which have the same statistical property, but which are mutually independent. So you know that the process that you have is Gaussian. So the amplitude of the field is a Gaussian random variable. Of course, we are dealing with the intensity. So the intensity is not Gaussian. For instance, this is a distribution of intensity. But anyway, because we have this theorem, I don't know how to call it, the Wick moment theorem or something like that, that tells you that when you have a Gaussian process, then all higher order moments can be expressed as a function of the second order moment, okay? So we can express, for instance, the correlation function of intensity, which is fourth order in the field, easily as a function of the knowing that it is a Gaussian, etc., etc. And from that, calculating the autocorrelation function of the intensity, that is to say, of the disorder, we easily find that it's characterized by what we call the size of a speckle grain, which is lambda multiplied by L, the distance, and divided by pi d. What I mean is that we know exactly that. And moreover, cherry on the cake, even if the lens you are using here is not good, even if you have aberrations, you don't care, because the central limit theorem applies in all cases. So you don't even need to pay for an expensive lens for doing that. Isn't that beautiful? Although, of course, with the funds of the Simon Foundation, we can buy expensive lenses. Okay, now 1D Anderson localization. And here I see already some theories say, what's that, 1D Anderson localization? It's absolutely not interesting. Yes, it is true. For instance, a gang of four, these people say, okay, all states are localized in one dimension. So why bother? Well, when you are a theorist, you can, Prigogine and Altschuler in '89 say, well, there is some interest in 1D localization, and this is my naive vision. Let us first consider this situation here, where I have, peaks. So I have a kind of strong disorder, and I have a particle with an energy definitely less than the height of the peak. The particle is bouncing. It's localized. Of course, it's trivial localization, but it is localized. The theorem is true. Good. Now look at this situation. Now the energy of the particles is well above the energy of the disorder, which is here. So it's like a plane flying over hills, something like that. Well, you solve the Schrödinger equation in 1 day. It's not very difficult to do. And this is what you can find. You can find localized wave function. And this smells like Anderson localization. Because if you want to understand that, this is due to the many scattered waves from the various peaks. So it really smells like the Anderson localization. And we thought it was worth testing it. So this is how we do. I promised that I would show you how we do the experiment and some of the wonderful tools that we have. First, we do a speckle here, and we do it with a slit which is narrow along the vertical direction, which means that here we will have a disorder which is basically transversely invariant, not infinitely invariant, but invariant on some dimension. And because the atoms are confined here in a laser beam holding them, you remember the dipole force? We have a laser beam detuned to the ray, attracted the atoms towards the center of the beam. So the atoms are circulating in a kind of pipe here, and the disorder is broad at the scale of the diameter of the pipe. But along the pipe, we have a disorder like that. It's like that, okay? And here you have the order of magnitude of the size of the grain of speckle, 1 micrometer along the axis of the tube, and 50 micrometer in the other direction. Okay. So this is how we do the experiment. We start with a Bose-Einstein condensate, which is here. We hold the atoms in the Bose-Einstein condensate, and they have some repulsive energy. And at time t equals 0, we release the longitudinal holding. we keep the tube, but we have a kind of longitudinal potential. We release that. And so it's going to expand because you have repulsive energy, okay? And so this shown here, we start with a Bose-Einstein condensate, and we release it, and it starts expanding. And what you can see, you look at the radius of the sample that you observe after various expansion times. So you see the beautiful tools that we have. We launch a thing, and we flash a laser, and we observe the cloud. You repeat, we flash a little later, etc. And we have ballistic expansion, obviously. And you are going to tell me, come on, this is trivial. It's not trivial at all, because if you don't control at the nano-Kelvin range, it doesn't work. Any small, if it is not exactly horizontal, it will accelerate, etc., etc. Believe me, doing an experiment like that is fantastic. But being able to do that, then we could observe 1D Anderson localization, as I am going to show you. To make a long story short, why do we use a Bose-Einstein condensate? For the same reason that we can observe interference of diffraction with a laser beam. In fact, interference of diffraction is a one-photon effect. But in a laser beam, I have many times one photon. In the Bose-Einstein condensate, it's exactly the same thing. A Bose-Einstein condensate is many atoms all in the same wave function. Like all the photons are in the same mode of the electromagnetic field. So we are going to launch that, and what will be, this is very important, the maximum velocity of the atoms which are released. Well, initially, we have what is called the, well, you know what it is, the chemical potential, which is the interaction energy, which means that once it is expanded, all this initial potential energy has been changed into kinetic energy. This allows you to calculate the maximum momentum of the atoms propagating in the tube. Okay? And this is the result. No disorder, ballistic expansion. Disorder, zoom, boom. Looks like localization, you know? And you see the scale, after 1 second, it's localized. And you see here, this is a real photo of Anderson localization. Why can I do a single photon? Once again, because I have many times one atom. In books, in quantum mechanics, they will tell you, you launch one atom, you make a photo. You launch another one, you make a photo. You launch another one, and you repeat 1 million of times, and then you rebuild the histogram. But here, we have the whole histogram in only one photo. Okay, and so this really, I love this photo because it's the first time, I think, the first time ever somebody could see a localized wave function directly. Okay, do we have exponential localization? The answer is yes. You see here that it is an exponential? No, you don't see it, so let's plot it in semi-log, and you see that indeed we have exponential localization. We can determine the localization length. We can compare it to the theory, which is quite simple because basically it's first-order calculation, etc., etc. Okay. So this was the first step of our program, done with Laurent Sanchez-Palencia, who is in the room. So if you want to know more about what I say, it's an easy calculation. Ask him. He will tell you that indeed it is an easy calculation for him. Okay. Now, we observe something strange. There was something like an effective mobility edge in our experiment. In other words, when we weren't changing the initial energy of the atom, which transfers into the kinetic energy, it turned out that localization worked only when the energy was small enough. How can we have a mobility edge in 1D? The theory doesn't tell us this. Well, you will see. So we observe that, in fact, we observe localization only in the case when the maximum momentum is smaller than h divided by the size of the grain of speckle. How to understand it? Well, we have to give a naive image of what is 1D localization in a weak disorder. It goes back to you can interpret it by considering Bragg reflection. You know what is Bragg reflection? You have a particle. Non, ça marche pas. C'est comme ça. Voilà. You have a wave arriving here. If the momentum is exactly equal to h bar k divided by 2, where k is a k vector of the wave, which is here, you will have Bragg reflection. And when it goes back on the left, you also have Bragg reflection, which means that this wave cannot propagate. Okay. Now, what is a disorder? A disorder, you can decompose it in many waves with many k components. And so that's the idea of Anderson localization. In 1D, whatever the velocity of your particle, there is only a grating that reflects you and prevents you from advancing. And so in order to have Anderson localization, this demands a broad spectrum of disorder potential. And indeed, you have a broad spectrum if, for instance, you consider the beloved model of theorists, which is a model in which you have peaks, so the autocorrelation function is a Dirac peak, and the spectrum is flat. So if the spectrum is flat, whatever your velocity, you cannot proceed. This is Anderson localization. But in our case, our potential, our disorder, has a finite autocorrelation function, which is something like that. And as a result, the Fourier transform is limited like that. And so it's only waves with a k vector small enough that will be impeded, or that cannot proceed. Okay. More precisely, and this was a work of Laurent Sanchez Palencia. More precisely, when you calculate seriously the autocorrelation function and the spectrum of the frequencies present in this disorder, you find a cutoff. This cutoff has an easy interpretation. It comes from the fact that the maximum frequency, spatial frequencies that you can have here, depend on the opening of the beam here. The fastest oscillation you can have is from a wave arriving like that and a wave arriving like that. So you have a cutoff. And now you understand, if you launch atoms with a k vector which is bigger than that, it will not be localized. If you launch them with a velocity which is less than this effective mobility edge, it will be localized. That's the explanation. What is the conclusion? The conclusion is, well, this is just to show off and show that we can do sophisticated theory and calculate everything. I have no time to elaborate. You can ask questions if you want. But the lesson which I want to emphasize is that when you introduce a new parameter, which is the correlation length of the disorder, it allows you to observe new phenomena. And there are, in fact, in this equation of Anderson localization with correlated disorder, there are several phenomena which depends on the fact that we don't have Dirac peak, but that we have a correlated. So the problem is richer. Okay, let us go to the next problem. Of course, after 1D, we wanted to observe 3D Anderson localization, and it worked. This is how we did. You remember the experiment in 1D consists of having a Bose-Einstein condensate, and you let it expand. And you don't have problem because you hold the atom in a laser beam, which is horizontal. But in 3D, you cannot hold them with a laser beam. But we could anyway hold the atom, not going to rocket, just in the laboratory, because our atoms are paramagnetic. They have a permanent magnetic moment. And by using a gradient of magnetic field, you can hold the atoms in the vertical direction. So first, we hold the atoms. Even if we release them, they are held. Second, we want a three-dimensional disorder. And to construct the three-dimensional disorder, we use two crossed speckle with coherent beams, so that when you calculate it, you have some advantage compared to two independent speckle. Boy, I don't go into the detail, but the result is interesting. The size of the autocorrelation function along the various axes is 0.11, 0.3, and 0.08 micrometer, which is good, but it's not isotropic. A good point also, because we studied that carefully, is that the classical percolation threshold is very low, which means that if we observe localization, you cannot tell me that we were just classically trapped, okay? With all that, we embark into the experiment, and here is the result. At time, remember, at time t equals 0, we release the atoms and we observe the expansion. With a weak disorder, this is what we observe. Hop. The density, ça marche pas très bien, hein, ça. The density decreases, and finally it disappears. And if you observe the dimension, it's just a diffusion thing. It goes at the root of time, etc., etc. But if the disorder is strong enough, there is a component that disappears, but there is a component that remains after 6 seconds. You should realize that 6 seconds with atom is almost infinity. Okay, it's amazing. And after 6 seconds, there is still a component. So obviously, there is a localized component. This is what we observe here. We look at the density at the center. In the weak disorder, goes to 0. And in the strong disorder, you have an asymptote, and this asymptote gives you the localized component. And we try to make sense of that. And then comes the problem. Because when we try to make sense of that component, after doing many experiments, we realize that we have a basic problem, which is the following. The way we do the experiment is the following. We have a Bose-Einstein condensate, and at time t equals 0, we release the trapping and we ramp up the disorder. And because localization works only with strong disorder, this ramping up provokes a wide spread in the energy of the atoms. And in fact, when you look a little in details, you find that whatever you do, whatever the parameters, you are in a situation like that where you have a broad energy distribution which covers above and below the mobility edge. And so if you really want to know what is the mobility edge, you need to go for a deconvolution, which we don't consider very safe because it's too broad, okay? You have uncertainties in an experiment. Okay, that's the way it is. So a new experimental scheme is requested, and it is at this point that we entered the collaboration. So we wanted to implement a new method for doing quantitative studies, and this method will consist of loading the atoms in the disorder at a well-defined energy. Rather than ramping up the disorder and we have a mess, what we decided to do is to start from a level here, which is not affected by the disorder, and do a transition to level 2, and the level 2 is sensitive to disorder. So the first realization of that consisted of taking a laser speckle on this transition, and you see when it is slightly below the resonance here, I told you it's a repelling. So you have a potential which is repelling here. And here in that state, basically, because the detuning here is large enough, you see the order magnitude. 7 gigahertz here only 80 megahertz. So the effect of the speckle is 100 times more important here than here. And so it worked, but we have a problem. The problem is that because here the detuning is quite small, there is also spontaneous scattering of photon. And spontaneous scattering of photon destroys the coherence of the waves, and Anderson localization is about coherent waves. And the lifetime was order of 10 milliseconds. And 10 milliseconds is not enough to observe Anderson localization. You saw we need seconds to observe it. What to do with that? Well, we did a nice experiment, which was probably one of the first significant papers published in the frame of the collaboration. We measure the spectral function. I don't go into detail, but the spectral function is what characterizes the distribution of energy of the atoms when you load them in a disorder. And you see here it's really beautiful because we have made precise measurements thanks to our new method, and we have precise calculation, and we can compare the result of the measurement both to the calculation of Dominique Delalande and also to calculation done with the landscape method. So this was one of the first significant publications with the collaboration. You see, it's long-term, okay? Experimental physics is slow. So we were not happy because there was this scattering of photons. So we decided to use, Svetlana mentioned it, a method using two speckles, bichromatic speckle. What did we do? We have now two lasers. This laser provokes a repelling potential here, but this one provokes attractive potential, and we tune them so that they compensate here. But when you look at this, both are repelling. So in the ground state, we have basically no potential, disorder insensitive, but in the upper state, it's disorder sensitive. And now the detuning are big enough, here you see 1 gigahertz, and here yet more, okay, that there will no longer be any scattering of photons. Okay, and now you see the lifetime is 1.2 seconds, which is good. And now we are ready for measuring the mobility edge. Now, what was the situation when the collaboration started? There was our experiment of 2012 in which we hesitated to make a deconvolution, but anyway, we had done some kind of deconvolution, and we say that our data were compatible with something in this region. We had colleagues in Italy who had done careful measurement and deconvolution also, and this is what they announced. And this is the result of the calculation of the Delalande group, assuming an isotropic disorder, but demonstrating more or less that they can do an equivalent, something equivalent to our anisotropic. And there was also a group in Chicago, but I cannot represent it because it was 10 times higher. Okay, it's off shale. Okay, this was the situation. So we did our first measurements, and here are the points. They come exactly on the curve calculated by the theorist. So we were really excited, okay? And Svetlana already showed this curve. As she said, it really looks like a phase transition. You know, what we do is that we change the value of the energy that we load into the disorder. When it is below the mobility edge, it stays. And when it is above the mobility edge, you have diffusion. This is what we measure here. We measure the expansion. No expansion means localization. Expansion means diffusive. And so you see, we can point out easily. But to be honest, there was a problem. This was clear only at a well-chosen time. Beyond that time, even the so-called localized thing still was evolving. So we knew there was still some problem. And because we are honest people, we did not publish that at that moment, and I think it was a good idea. It was a good idea because we found another problem that demands a sophisticated solution. First, what we did is switching off the red laser once the atoms are transferred, because the disorder of the upper level can be totally done by the blue laser. And so we increased the lifetime of the atom in the disorder, and with that we had new results, and you know that these are long experiments, okay? But you have one here, one here, one here, one here. Very good. But these people, Shudong is around. Where are you, Shudong? Ah, he's here. You will ask him. He spends nights in the lab, okay? And it's a difficult experiment. But by checking everything, he saw that there were unexpected losses in the laser. So yet another problem, okay? Okay. They work hard, and after some time, they find what may be the solution or the reason for this loss of atoms. These are the various levels which are involved, and in fact, what we do is working with that level, which is here. Doesn't matter, but we work with that level. But the problem is the following. You may have collision between two of these atoms which give one atom here and one atom there, because it is a collision which is conserving the spin. You know, you go from spin 1 to spin 2 and spin 0. So this collision is allowed, and although you have extremely slow atom, it's allowed to have such a collision. And as soon, so which means that you have atoms which leave the level where we want to have them, it destroys the coherence, etc., etc. And so they found a really sophisticated solution, which is the following. Invert the level scheme. Go from this upper scheme, which is from this upper level, which is here, to that one. And in that one, you have no possibility to efficient cold collision for quitting it. And they did that, and in that situation, you have no more inelastic collision. And with that, they say, we are going to do more measurements. And in doing more measurements, they found the cherry on the cake. Maybe. This is maybe the cherry on the cake. What they observe is that with the experiment, which is now at its ultimate sophistication, okay, you look here at the profiles as a function of the position in the disorder. Here it's above the mobility edge, and here you are below the mobility edge. And when you look carefully, for instance, at this, you observe some structure here. There is a patch and another one here also. Well, you say, wow, what's that? Well, what is interesting is that if you observe it at various times, it seems that these structures are always at the same place. Hence the question, could it be atoms localized in one of the structures of the landscape? We don't know yet, but this is very exciting, and I think that it is a beautiful conclusion for this collaboration. You know, all these years and all this help of the Simons collaboration have allowed us to, and of course all the people who have worked on that, have allowed us to arrive at this very sophisticated experiment where now we can hope maybe to observe directly the atoms in the structure of the landscape. So what I want to do is, first conclusion, cutting-edge experimental program is full of bad and good surprises. It was a long journey, permitted by the support of the Simons Foundation, and once again, we could not have done that without the significant support of the Simons Foundation. The journey continues. We are going to make many more quantitative studies of the critical parameter for comparison with calculations. And we have the possibility to study this possible relationship between the speckles that we propose and the landscape that they can calculate, because now there are new techniques that we have not yet implemented. Rather than having just a scattering plate, we can have what is called DMD. DMD allows you to do dynamical holography and to tailor, in a sense, the kind of disorders that we have. This will be a beautiful program. And so thank you, Svetlana and Marcel, for embarking us with this group of wonderful people in the collaboration. Thank you very much.